Welcome to Spring LIB.
All right, so kind of a tricky question here. Number 9 is, it's about length contraction and time dilation, of course, and special relativity. So you have that a friend is speeding by you at velocity 0.72 c, okay? And you measure, and it is you measure in your frame that the length, which I'll call L, is 4.85 meters. So this is the length in the direction of motion of the ship, and so this is what will be length contracted. This is the length that will be shorter when you. This is the length that is actually shorter in a moving frame, right? And the height of the ship, let's call it H, is 1.35 meters, and so this length is perpendicular to the direction of motion. So this will not be this length will not be different regardless of which frame you measure it in. So this is what will change. And so the first part, part A. Okay, before I write down an equation, very important to note here is that though not explicitly stated in the problem, we are assuming here that the frame of your frame, that the stuff that you're measuring is in a moving reference frame, okay? And that will change a lot of things compared to if you were in a rest frame, such as the rest frame of the Earth, right? Okay, so we start off by using equation 26-3a, which is the length contraction formula, and it's given by L. The measured length equals equals L naught, which is the proper length, proper length, the rest length, times 1 minus v squared over c squared. Okay. And so L naught is what you want here. L naught is just L over this 1 minus v squared c over c squared stuff. And so, okay, so that's L naught. And we have that L is 4.85. Remember, the height is not going to get shorter. Over 1 minus, notice that V is 0.72 c. So if you take 0.72 squared, you effectively get V squared over c squared. So 1 minus 0.72 squared, and that gives you 6.92 meters for the rest length. And that is the length and height. That's the measured length. That's the rest length. And H naught, the rest height, will be the same as the measured height in a different frame, which is 1.35 meters. So no changes there. Okay, moving on to part B. Here we use the time dilation formula, which is a statement that moving clocks run slower than clocks at rest. Okay, delta T naught. This, remember, is the proper time. So this is the time we want here, is delta T times 1 minus v squared over c squared. Okay, so here we're noting that 20 seconds pass on your own watch, and if your frame is a moving frame, then the proper time will actually just be the delta T naught. So delta T will be 20 seconds multiplied by 1 minus, again, 0.72 squared. And this works out to 13.9 seconds. So as expected, on her watch, she's moving close to the speed of light. Time will move slower. Okay. Part C. How fast did you appear to be traveling according to your friend? So this is where we use a very central idea of special relativity, which is that relative speed will be the same as your friends. And so remember, no matter what reference frame, relative is the key word. Relative speed is measured. You will measure the same speed, right? So therefore, v will be the same as how fast your friend appears to be moving relative to you, which is 0.72 times the speed of light. Okay, so it's the same speed. And part D, again, we'll use this equation and we will again get the same answer, because remember, you're moving relative to your friend at 0.72 c, so the proper time, again, is a dilated time, and so this again is 20 times 1 minus the relative speed of yours, which is 0.72, and all of that is the same thing as part B, so that's 13.9 seconds. So kind of a few tricky nuances that you have to think about in this problem, but it's not impossible to work through them. And that's it.